Welcome pre-calculus students to another lesson in our unit of exponential functions and logarithmic functions. For today's lesson, we are actually going to be moving on to graphing log functions. We haven't done graphing in a while. The last time we did graphing was when we were looking at exponential functions, but now we will be analyzing how to graph a log function, and we're actually going to end up going over multiple methods in terms of how to graph a log function. The first method that we're going to be talking about today is this idea of being able to use the inverse relationship between a log function and an exponential function to help us actually draw a log graph as opposed to an exponential graph. So let's get started here. So our goal for this lesson is to be able to graph the function f of x is equal to log base 3 of x minus 7 plus 2. Okay, so we're going to, at the end of this lesson, we will be able to graph that function. And like I said, the first method that we're going to be using is using the inverse function in order to arrive at the graph. We're going to be looking at more than one method, so this is not going to be the only way or the only manner in which we can produce a log graph, but this will be the first method that we will be covering. So first, let's try to find the inverse of this function. All right, let's try to find the inverse of this function. Now, first off, recall that we've talked about this idea of what is the inverse of a log function. The whole point of a log function to begin with was the fact that it was the inverse of the exponential function, right? The log function was just the inverse of the exponential function. So if we had a function such as, I'm just going to make one up here. Let's say we had a function such as g of x is equal to 2 to the x power. The inverse of that function would be g inverse of x is equal to log base 2 of x. All right, so they're inverses of each other. Now, once again, since log is the inverse of exponential, the reverse is also true. Exponential is the inverse of log. So we're going to use that idea to try to determine, well, what is the inverse of this function that we have, which is log base 3 of x minus 7 plus 2. So let's do that. So the first thing, if you recall, so this is a little bit of a review of what we've done in the past, which is being able to find the inverse of a function. If you recall, in the first unit of our school year, we talked about this idea of how do you find the inverse of a function algebraically. So typically the first step that we would always do is we would turn this into y equals instead of f of x. So I simply replace the f of x, or the function notation, in the equation with a y. So I'm going to write our equation now as y equals log base 3 of x minus 7 plus 2. So that's the first step. So nothing too complicated so far. So now recall the second step is we're going to try to get the x variable, in this case, trying to get the x variable by itself, right? So instead of y equals something, we're going to make it into x equals something. So let's get the x variable by itself. So just as you would follow the typical steps in the past when we were solving these equations, right? You would try to get the variable by itself. We're going to do the same thing here. So we're going to be moving stuff around this equation. We're going to be doing things at both sides of this equation in order to get x by itself ultimately. So the first thing we're going to do to both sides of this equation is we're going to get rid of this plus 2. Okay, so we're going to get rid of this plus 2 by subtracting 2 from both sides. All right, so let's just subtract 2 from both sides. And actually, let's make this step 2. Okay, there we go. So let's see. Our new equation so far is y minus 2 is equal to log base 3 of x minus 7, since we got rid of that plus 2. All right. So at this point, we can't do anything to the expression inside the parentheses, so we can't do anything to the minus 7 yet. We got to get rid of the log now. We have to get rid of that log expression. Now, once again, the inverse of log is the exponential function. So what we're gonna do here is we're gonna make both sides of our equation into exponents. Okay, so we're gonna make both sides of our equation into exponents. So we're gonna make the left side y minus 2 into an exponent, and we're gonna make the right side log base 3 of x minus 7 into an exponent. And the base of our expressions is going to be 3. And once again, we made 3 our exponential base. We made base 3 our exponential base because we want that log to cancel out. In order to cancel out a log base 3, you have to use a base 3 in order to cancel it out. So now the right side cancels out. So we move on to the next point in our problem. The left side is just 3 to the power of y minus 2, and the right side is just x minus 7, since the log base 3 canceled out, so we're just left with whatever was inside the parentheses, so in this case, x minus 7. Okay, so we're almost there. We almost have the x by itself. We still have that minus 7 to take care of. Now, to get rid of that minus 7, we're going to add 7 to both sides. To get rid of that minus 7, we're going to add 7 to both sides. So that gives us 3 to the power of y minus 2 plus 7 equals x. Because that minus 7 and plus 7 cancel out. Now, really quickly, one comment I want to make is careful. When you're adding 7 to both sides, you're not adding it to the exponent. So you're not adding it to the minus 2. Right? It's not y minus 2 and then the plus 7 to the minus 2. No, it's added to the entire expression because, once again, we're adding the plus 7 to the entire expression. We're not adding plus 7 just to the exponent. So be careful there. Do be careful there. So we got the x by itself. Which was our goal. All right. So that was step 2, getting x by itself. Now, step 3, if you recall, is a really easy step. Step 3 of finding the inverse of a function is you just switch the x and y variables. Recall that when you have two functions that are inverses of each other, you end up switching the x and y variables at some point in your process. So I'm going to change this into y equals 3 to the power of x minus 2 plus 7. So I simply just replace the y with an x and the x with a y. Nothing special there. And then if you recall the very last step, and this step is not really as important when it comes to this idea of being able to graph this eventually, but if we wanted to be proper, our last step would be to actually write it using the appropriate notation, which is, since we're trying to find the inverse, recall, we write it as that f negative 1 power, or that's what it looks like, but that's the notation that we use for inverse, is equal to 3 to the power of x minus 2 plus 7. So we have successfully found the inverse to this original function. Okay, so the inverse of log base 3 of x minus 7 plus 2 is 3 to the power of x minus 2 plus 7. So that's the inverse. So that's 1. That's the first thing that we do. And you'll see why in a second. So that's the first thing that we do. All right. So, 2. Graph the inverse of f of x. So the function from number 2. Okay, so we're going to graph the function from number 2. So the function from number 2, which I already forgot, function for number 2 was, just a reminder, 3 to the power of x minus 2 plus 7. That was our equation from number 2. Or, I'm sorry, number 2. Typo here. This should say the function from number 1. All right. Because that's where we found the inverse equation. So at this point, what we're going to do, we're going to graph this equation. Okay, so we're going to graph this exponential equation, which we've done in the past. At this point of our unit, we've graphed exponential equations before. And if you recall, the manner in which we've graphed exponential equations is we've just plugged in x values. Nothing special, we just plugged in x values. If you recall, typically, I would have you guys plug in both negative and positive x values. So let's do that for the purposes of this demonstration. So let's do -1, 0, 1, 2, 3, and 4. But remember, it does not matter which x values you pick, but typically I have encouraged you guys to pick both negative and positive x values. You don't necessarily have to, but remember, if you do have a better chance of getting a nicer picture of your graph. If you don't, you run the risk of getting a incomplete drawing. Because remember, an exponential graph is a curve, and you do want that curve ultimately when you draw it. And if you don't have that curve, that means you probably did not pick x values, appropriate x values to get your nice points. Okay, so at this point, I'm going to plug each of these x values into the equation. So let me, and just for demonstrations purposes, I'll do the first one, just so that we're clear on how we get it. So the first one would be, tablet is moving all over the place. So the first one would be, come on. And there we go. So the first one would be 3 to the power of negative 1 minus 2 plus 7. Okay, so you do the exponent first, so negative 1 minus 2, do the exponent first. So that's negative 3. So this is the same thing as 3 to the negative 3 power plus 7. So at this point, you could just plug it into your calculator. So 3 to the negative third plus 7. So you should end up with, let's see, I'm pretty sure I know what it is as a fraction. So as a fraction, it would be 7 and 1/27. So 7 and 1/27, sorry, that should be a 2, which is about, let's see, as a decimal, all right, there it is. And then, so it's about 7.04, so 7.04. Okay, and then we're just going to continue that with the rest of the x values, doing the same thing. So f of 0, f of 1. I'm plugging my values into Desmos, but once again, you could just do this in a calculator. You end up with the same thing, but I typically do encourage everyone, if you don't have a calculator, you can always use Desmos. So for the rest of the values, you should end up with 7.11, 7.33, 8, 10, and 16. So those are the values you end up with if we plug in our values into the inverse function. So at this point, we're going to graph it. This point, we're just going to graph it. So let's see, negative 1, so 7.04, it's about here. I'll do my best here. 0, 7.1, 1, 7.3. It's not going to be perfect, but at 2, it's 8. At 3, it's 10. And then at 4, we can't even fit it on the graph. So once again, sometimes there are times in which you might get points in which you can't draw in the actual coordinate grid in front of you, and that's okay. That's okay. We can't fit 16 because we only go up as high up as 10. So now we draw our graph, and once again, we should get a curve. If you don't get a curve, that means something went wrong. There you go. We end up with our curve. If you recall, this is a growth function because it is always increasing. This is a growth function that is always increasing. And don't forget this next part. All exponential functions have if you remember that invisible line, horizontal line, that the graph gets closer and closer to or approaches as we go in a specific direction, horizontal asymptote. So if you guessed horizontal asymptote, good job. Don't forget about that. The horizontal asymptote. Horizontal asymptote at y equals 7. Yeah, don't forget that part too. Remember, all exponential graphs do have a horizontal asymptote, and that's going to come into play as well when we graph the log graph as well. Okay, as this graph goes to the left, it gets closer and closer to y equals 7, but never touches it. And hence, that's why it's an asymptote. Okay, so we graphed the inverse function, which was an exponential function because that is the inverse to a log function. So you might be wondering, okay, how does this help us? How does this help us to actually graph the actual function? Well, let's go to the next part. So number 3, use the graph/table from number 2 to graph the original function. So why did we do the graph/table in the previous slide? Well, this is where knowing the relationship between inverses comes into play. Recall that the one convenient part about graphs that are inverses of each other, I'll give you a few seconds to think about it. If you remember what you actually, what is true about inverse graphs is that the graphs of inverse functions, their points are just reverses of each other. Okay, you just literally switch the x and y values and boom, you have the points for the respective graphs. So in the original table, let me see if I can try to remember these off the top of my head. Actually, I'm just going to redraw it here. There. So I don't have to keep on switching back and forth. So in the inverse table that we just did in the previous slide, the inverse table that we just did in the previous slide, we had negative 1, 0, 1, 2, 3, 4, 7.04, 7.11, 7.33, 8, 10, and 16. Okay? Well, since we did that table already in the previous slide, we can easily do the original function table now. Because once again, since they're inverses of each other, all we have to do is just switch the points. So instead of negative 1, 7.04, we have 7.04, negative 1. Instead of 7.110, 7.11, I'm sorry, instead of 0, 7.11, we have 7.110. So we just switch the x and y values. We just switch the x and y values for each of the points because they're inverses of each other. That's why this method is a little bit convenient, since once we find the points of the inverse function, we just switch the x and y values and boom, we have the points of the actual function. Okay, so once again, this table that we just did is the table for this equation, for the original equation. Okay, because in the previous slide, this table was for the inverse function. But ultimately, remember, and this is why I put this on each slide, our goal is to graph this one, okay? Is to graph this original equation. I mean, all we did in the previous slide was we just graphed the inverse of the function equation. That's not our ultimate goal. Our ultimate goal is to graph this function equation, okay? And once again, by switching the x and y values of the inverse function, we were able to find a table or construct a table for this actual function equation. So now we just plot the points. So let's see, 7.04, negative 1. Put that there. 0, 7.1. Well, actually, let me use a different color so that... and actually, just so that it's clear that this is a different graph, 7.04, negative 1, 7.110, 7.331, 8.2, 10.3, 16.4. Okay, so these blue points are for this function, this f of x function that we originally started out with. So 7.4, negative 1, 7.10, 7.31. Yeah, I'm good. For a second there, I thought I made a mistake. 8.2, 10.3. And then once again, 16.4 we can't fit because our x values don't go that. All right, so let me get my curve there. There we go. And again, hopefully you can see my points. They're a little bit hard, but they're definitely there. Okay, so that's our new graph. So this blue graph is the graph of this log function. Okay, so this blue graph is the graph of this log function. So congratulations, we just graphed our first log equation by using the inverse equation. Okay, and you might be wondering, well, something's missing here. Because remember, in the previous slide, we didn't just draw the graph. Go to the previous slide here. We didn't just draw the graph. We also drew the asymptote. Where's the asymptote for this graph? Some of you might be able to figure it out just by looking at the picture. There is an asymptote for this graph. So first, recall that in the original function, in the original function, for the inverse function, the asymptote was y equals 7. right? We wrote it down, y equals 7, horizontal line. Well, remember, what do inverses do again? They switch the x and y values, right? That's the whole point of inverse, or that's the relationship between inverse graphs. They just switch their domain and range, their input outputs with each other. So in this case, x and y. Well, what happens if we take y equals 7 and we just switch it? So originally it was for the inverse it was y equals 7, but what happens if you switch the x and y? It becomes x equals 7, right? If we just switch the y with an x, right? If we just switch the y with an x. Well, what does that look like? What does x equals 7 look like? Well, x equals 7, for those that recall, if you were actually to graph it, x equals 7 is a vertical line. That's what x equals 7 looks like. It's a vertical asymptote now. We don't have a horizontal asymptote anymore. We have a vertical. So it's at, if I were to draw it now, you're going to have an asymptote at x equals 7. Okay? Because for the inverse, we had y equals 7. So if inverses just switch x's and y's with each other, it becomes x equals 7 now for the original function. It becomes x equals 7 for the original function. And x equals 7, if we were to graph it once again, is a vertical line. It's not a horizontal one anymore. It's a vertical line. Okay? So we would say a vertical asymptote at x equals 7. So that's another thing you got to remember for these log graphs. We're not going to have these horizontal asymptotes anymore. Now we have a vertical asymptote. Okay? And now this time, because remember with the horizontal asymptotes, we always talked about this idea of being able to explain why it's a horizontal asymptote. Well, this time around, to explain the vertical asymptote, right, if you notice what's happening is because as f of x approaches or gets closer and closer to, however you want to word it, as f of x approaches x equals 7, the graph goes down forever. Okay, so as f of x approaches x equals 7, the graph goes down forever, or goes to negative infinity, right? Right, if we look at this graph, as it goes down, let me see, I think there should be a, no? Could have sworn there was a laser pointer here, but maybe not. As this graph goes down, I apologize. As this graph gets closer and closer to this vertical line, which is x equals 7, right? So as it gets closer and closer to x equals 7, it just keeps on going low. It just keeps on going more and more, becomes more and more negative. So it just goes to negative infinity, or it just goes down forever. So that's how we have basically the opposite. Uh-oh, what just happened? My slide just disappeared. Yes, keep. Apologize for that. Just decided to exit out on me. So this time, in the past, we always said, well, as it went to the left forever, as it went to the right forever, the graph got closer and closer to y equals whatever. This time, it's basically the reverse. As the graph, or as f of x approaches x equals 7, or gets closer and closer to some x equals number, the graph is going to go down or up forever this time. Okay, so it's a little bit different. Instead of in the past, when we would look at going to the left or right, now you have to think about this idea if it's going up forever or down forever. And obviously, you'll see other examples that'll make you hopefully understand it. So let's recap. So what did we do? So the first thing that we did is we found the inverse of the function. So we just followed the same steps, put it as y equals, got x by itself, and then that was the first thing that we did. Second thing that we did we graphed the inverse of the function, which technically we didn't have to do, because if you recall, once we got to step 3, we actually just used the table. We didn't actually use the graph, but sometimes it's nice to see the graph. But ultimately, this was important, being able to construct this table for that inverse function equation that we found. So that was step 2. And then finally in step 3, since they're inverses of each other, we just switch the x and y values. Since they're inverses of each other, we just switch the x and y values, and we just plotted the points. And once again, this time, instead of having a horizontal line, we have a vertical line. Because once again, since the x and y values switch, when you have x equals a number, that represents a vertical line. Okay, so we don't have a horizontal asymptote anymore, which was y equals a number. We have a vertical asymptote now because x equals a number. All right. So this next slide is just basically talking about just this idea of vertical asymptotes that we just talked about, that since log functions are the inverse of exponential functions, they will not have horizontal asymptotes, but rather vertical asymptotes. Okay, so now this time, the graph is going to be going down or up forever as it approaches some x value. Okay, so the graph is going to be going up or down forever as the graph approaches some x value. And that's the definition. That's the definition of what a vertical asymptote is. Okay, so the definition of vertical asymptote is as your graph approaches some x value, it will continue going up or down indefinitely, or it will continue to infinity, to positive infinity or negative infinity, however you want to describe it. So once again, instead of y equals a, so remember, whenever you see an equation y equals some number, that represents a horizontal line. But now, since the x and y switch for log graphs, we end up with a vertical line. Okay, so just recall that the equation of a vertical asymptote is now going to be x equals whatever number that you're getting closer and closer to as you're going up or down indefinitely. All right, and then this example 2. Okay, this example 2. So this example 2, I actually want you guys to try on your own. So please do this example 2 on your own, just following the exact same steps that we did, so you can easily look back through the video to see what we did exactly, and hopefully everything goes well. Obviously, you can always let me know if something does not churn up correctly, but it should hopefully go smoothly. All right, so that's basically it for today's lesson. So that was method 1. Eventually, like I said, we'll look over there's going to be another method that we're going to look at. I'm trying to remember if there's a third method. I think there was, but I don't think I was a huge fan of it. But there's definitely a second method that we'll look at into how to graph log functions. Otherwise, let me know. As usual, however you want to reach out to me, let me know if you have any questions on any part of the video or the lesson. And hopefully I can provide some feedback on whatever work you end up submitting. Otherwise, I hope you guys enjoy the rest of your days.